Hi, good afternoon, everybody. My name's Ian Morris. I'm an applications engineer with the RF Connectivity Solutions group at NXP. So I specialize in what people commonly refer to as Zigbee technology, right? 802.15.4. But today we're going to take that a little bit step further, and we're going to introduce NXP's new mBed Thread platform, okay, based on 802.15.4. So let's get started. So the IoT, very kind of overused term, in my opinion, and probably everybody else's opinion here at the moment. But it's something we have to mention on our slides, right? Because that's why everybody's here, because they want to learn about how to connect things to the internet. So it is the Internet of Things. What we specialize at NXP is really at the moment the smart home. And that's particularly relevant because that's really a good synergy with what the Thread group are trying to do. Okay, they're promoting their wireless communication technology initially at smart home applications, okay? And so smart home, what do we mean by that? Well, there's a multitude of devices that can be connected, okay? So we as NXP started out in the Zigbee space, and we were doing things like connecting light bulbs and sensors, et cetera. But that's really grown now, and we support BLE, and now with the onset of Thread, we support IPv6 technology. So we can connect most things in the home that require low power, low data rate communications. We've got the wireless communication technology to connect those. We've got a lot of the sensor interface technology that is behind those devices. We've got a lot of technology that we can use in the gateways, okay, so high-end microcontrollers. We've got secure element technology that can make all of this much more secure. And then finally, we've got NFC technology that can make this easier to commission, easier to add devices into your network, and easier to do it more securely without adding complication for the end user. Okay, so here's the things we started out focusing on, really. We started out in the smart lighting area as NXP, Zigbee. And really we did that because we have a strong kind of track record in lighting drivers. Okay, so that seemed to be a really good place for us to start and add our wireless communication technology. But we've gone right through building automation, and we're really big in smart energy, so connecting electricity meters now. Okay, so these are classical, more Zigbee opportunities, right? And we'll see the progression to Thread in the marketplace. This is a really important thing that we focus on now. Regardless of the technology that you use to connect devices, one of the big challenges is connecting them when the consumer gets them back in the home, okay? Because a lot of these devices are very simple, and they don't have a rich user interface. So you think about it, when you get a new laptop at home and you want to connect it to your Wi-Fi access point, it's pretty easy, right? Your laptop's got a keyboard, it's got a screen, it makes it easy to enter the key. If I'm trying to connect a light bulb or a door or window sensor, okay, that doesn't have a user interface. So how do I get the key into that device securely, okay? Very, very difficult problem to solve. So a lot of vendors or a lot of protocols, things like Zigbee, have come up with techniques to do it, and they're very effective. But what we can do is, using our NFC technology, we think we can make those techniques more secure and more convenient. So what we do is we embed an NFC-enabled memory into your end device, so something like a light bulb or a light switch. Okay, and then in the gateway side, we have what we call an NFC controller. So that's an NFC read writer that you find in a lot of cell phones, Galaxy cell phones, et cetera. And basically what you do is you take the device out of the box when you get it home, you tap it onto the gateway or onto your phone, and at that point, the information about the network you're joining is shared over NFC. So it's shared over this low data rate, this very low range, with no probability or very low probability of anybody being able to intercept that communication. So all of a sudden, I've shared my key into my widget that I'm going to join very securely. The other side of that is it helps ease of use, because it can be a two-way transaction. Okay, so what can happen is I tap the light bulb onto the gateway, but what happens is the gateway then learns, oh, you're adding a light bulb. So in your user interface, it can bring up a light bulb. So all of a sudden, I've tapped the device, it appears in my GUI, and also it's on the network securely, and I just go and screw it in and use it. So it's all about improving the user experience with NFC technology, and that can be applied to Zigbee, to Thread, to BLE, to Wi-Fi, to whatever communication technology you're using. So that's why we just wanted to mention that. Okay, so here's the things we're really talking about today. NXP's got quite a long history in the wireless microcontroller business. So back in, I think, 2006, we brought out our first 802.15.4 radio with a 32-bit RISC CPU. And up to date, we've always had a proprietary 32-bit RISC CPU. So the JN5179 that we announced at the show today, and that we'll be talking about, is the first time we've put a Cortex-M3 microcontroller into any of our 802.15.4 wireless SoCs. Okay, so it's kind of a big step change for us, and that's great. I mean, we did that for a number of reasons. One is the massive ecosystem that ARM has. Okay, so there's a ton of toolchain vendors, there's a ton of debuggers out there. But then there's the introduction or the respin of mbed. So now we have mBed-3.0, which is this complete software platform that we'll talk about, that we can leverage. Okay, and the idea being you can take our silicon, our Cortex-M3-based microcontroller, layer mbed software on top of it, and you can very easily connect your devices to the internet with minimum coding. Okay, so that's the 5179. These are our legacy devices, still supported, still shipping out in the field. We've upgraded to Cortex-M3 core in this device, and this is the one we've got in our booth. And then just a note for people that like looking into the future, ignore these dates. These are marketing dates, and we all know, things move out from what marketing predict. We've got a dual mode device coming in the future, so a BLE 15.4 combo. So this is a single device with both a BLE radio and a 15.4 radio. And this is very interesting. There's a lot of interest from a lot of our customers because, to be honest, people always come up to me and ask, well, should I design my new widget with BLE or with a Zigbee radio? Who's going to win? And no one knows, right? No one knows. And often you can't influence that. You may be shipping to a customer like Comcast who may demand BLE, but another customer like AT&T may demand Zigbee. Instead of building two products, you can build one product and take our combo device. So that's the idea behind it. It's a hedge against who's going to win the part of the protocol wars, right? Okay, so this is our software roadmap because very obviously software is a really, really important part. I would say almost more important than the hardware, just because there's so much or so many different types of protocols that you can run, even on a 15.4 radio. That's all we're showing here. This is just one radio, and these are all the different protocol stacks, right, that you can run. There's Zigbee 3.0, which is the latest version of Zigbee coming out at the end of the year. There's HA 1.2, the home automation profile that's current, and that's what a lot of devices, if they say they're Zigbee right at the moment, they're usually HA 1.2. There's Zigbee Smart Energy. It's used in the utility industry. There's the newly announced Thread that we'll be focusing on a little bit later. And then, of course, there's BLE, and that was traditionally a point-to-point technology, and now there's BLE Mesh. So we've got a whole host of different protocols, networking protocols that we can support on just one or two of our chips. So basically, we can cover, hopefully, we like to think we can cover most application scenarios. Okay, so this is what we're really here to talk about. One of the things, our so-called Thread chip, so the JN51.7X series. The first device in that series is the 5179. So it's a fully embedded SoC. Okay, so it is just one die in there, and we've got embedded flash, embedded RAM, embedded EEPROM. Okay, we've got a really efficient 802.15.4 radio, because we've been doing this for a long time. So we've got 10 dBm output power, because we found we really need to increase the output power, right? A lot of people come to us and take our standard 3 dBm radios and then expect to be able to do, I don't know, several hundred meters or more, and it just doesn't work out. So we increase the output power in this device so we can cover a lot more applications. We've got a whole host of peripherals in there. The one I really want to highlight that's unique, I believe, to this chip is integrated switch mode power supply. So as I said before, we had a long history in light bulbs, so smart light bulbs. And the typical architecture would be a 3-chip architecture in a smart light bulb. AC-DC power supply, constant current driver for the LED string, and then your wireless SoC, okay? But by integrating the DC-DC, or part of it, into this chip, we can actually cut that architecture down to be 2 chips. So we can take the high voltage DC that drives the LED string, we can switch it down into the 3 volts or less that we need to run this chip. So that feature is unique to this chip. It's targeted at smart lighting, but I have no doubt whatsoever that people are going to use it for other applications as well. So it's really good to be aware that that's in there. That's a kind of differentiating feature. Then we have the standard peripherals. It's now becoming more like an LPC microcontroller, right? For anybody that's familiar with NXP, we've got ADCs, we've got PWM timers, things like that. So it's a fully embedded solution. So system on a chip, radio, microcontroller on there. Okay, so this is talking about the architecture that I was talking about earlier, where we went from the 3-chip solution right down to the 2-chip that we get on the 7X. And you can see the cost down. This is really of most interest to the guys in the smart lighting market. Okay, but like I said, I'm sure people will find good reason to use this in other applications. So we started out as some of you may know, we have a kind of a long history in the 6LoWPAN world. And I mentioned the name 6LoWPAN because that's a key part of thread technology, for those of you who don't know. It's one of the layers in the thread stack, and we'll go through that. And we have a long history. We started out in 6LoWPAN, so basically creating IPv6-based wireless mesh networks many years ago with a technology called GenNet IP, which was proprietary to NXP at the time. So we have a long history, and we understand what it takes to get the not only the WPAN side, so the wireless mesh networking side done, but how to bridge that and get into the LAN or the WAN, okay, so the wider area networks. At the time, we were running, we had our own application layer, okay, so we wrote that all ourselves. And what we managed to do was really scale this, okay, so we know now how to scale up to 500 nodes. I remember when Zigbee first came out, people looked at it and said, oh, it's a 16-bit address. So that means I can have 65,000 nodes on my network. No, right? Doesn't work like that. Absolutely doesn't work like that. And so people were then saying, oh, well, okay, maybe I'll just a couple of thousand. No. 500, you know, you may look at that number and go, oh, that's not that great. It's actually quite a skill to be able to get up to that number and be able to put up that up there. And we have big warehouses full of nodes that we do regression testing on, okay, and we do regularly test up to 500 nodes, which is quite an achievement, actually. Okay, so the key message is here that we have a lot of history in just wireless networking in general, okay? So not just on the mesh side, but also, as I said, very importantly on the bridge side, because this is the piece of the technology, the piece of the puzzle that gets you out onto the internet. So this is the thing that really connects your wireless devices. Whilst they can communicate all together fine using our great kind of mesh networking technology, you need strong software in the gateway side to be able to bridge out into the network. So we got a long history of this, but what we're going to show is the next generation where mBed brings a lot of this software in for us. Okay, so NXP Thread. So I'm assuming this is quite possibly the older version of mBed and not mBed-3.0, as that's been fairly recently launched. So the way I always think about the difference between the two, mBed, I always think the previous mBed was really just an OS and a set of online tools. Okay, it was more than that, but that's how I think about it in my mind. mBed 3.0 is really significantly more, in my opinion, and they call it IoT device platform. And what does that really mean? What it means is, apart from the hardware, they're providing all the pieces of software at every part in the chain that you need to connect a device to the internet and then be able to control it either locally or remotely. Okay, so you can say that, right? You can say that, and it's just a quick sentence. The amount of work and the amount of software and technology behind that is actually, quite staggering. There's a lot of stuff they've done, a lot of software they've developed, a lot of different pieces of the puzzle. So the software, there's tools. So they've developed some new tools to make configuration management easier, to make it easier for you to publish parts of your software, right? And then finally, really interestingly, they've gone further than most people, and they've actually got a cloud platform. So a key piece of technology for the Internet of Things, and we'll talk about a little bit about what that does. Okay, so the mBed device server, this is one piece of their technology that they bring. So what is this? This is their middleware. It's really a cloud platform. So what it does there, it sits and runs on a server, and it's the thing your devices communicate with out on the cloud. Then your control applications have a web API that communicates into the device server. Okay? So this is a bit like, if anybody's familiar with someone like Ayla Networks or Arrayant, or there's a whole host of M2M cloud platform providers. mBed device server is kind of similar to those applications. Now, it doesn't replace them because it's more the glue. So it's really the piece of technology that allows your device, once it's got onto the wide area network, to be registered up in the cloud and for other web devices to find it, okay? Because you can't find it directly on its own network. They've built this so it will work with other third-party cloud platforms as well. So if you're already using a cloud platform, you can interface that cloud platform to this one using their web API. So it doesn't restrict you from using anybody you might be using at the moment. Now, the nice thing about it is they have this thing called Embed Device Connector. Device Connector is just the device server, but a hosted version of it, really. Okay, so I can take Embed Device Server, and I can take their software, and I can run it locally, and our demo runs it locally on our laptop. I can choose to run it on my own servers, my own infrastructure. I can choose to run it on AWS if I want, or I can let ARM run it on their servers, and then it's called Device Connector. And I just connect my device up to there, tell it what IP address to go to, and there you go. And I think they give you can connect 100 devices up to this for free. I think you probably, if you sat through their presentation, you probably know better than me, right? And so that's a really great and easy way to get started. So what they're providing is this whole range of software that before I would have to either develop myself or go to third parties to get. And then I've got the problem. I've got to integrate that all myself. And I probably I'm not an expert in web APIs, in configuration of routers, things like that. So the Mbed client, this is another really key piece of software. This is the piece of software I always think it can either run on the gateway or on the connected device. So in the gateway mode, this is the thing that talks to the Embed Device Server for you. So again, I'm not writing any code in my gateway that talks to that server. The Embed Device Client does that for me. Okay? The other way I can use the client is if I developing something with a true IP connection, so something like a Wi-Fi-based smart lock, something like that. I can actually run Embed Client on that Wi-Fi lock, and it can talk through my existing infrastructure, IP infrastructure, all the way up to the cloud, at which point I write my app on my smart device to talk to the web API, and that's it. So I'm really only developing an app on a smart device and a little bit of application code to run in the client framework, and I've got a thing that's connected to the network. And of course, the really important part, Mbed OS. So they still have their operating system. So it's a single-threaded, event-driven. Okay, so they've not gone with a multi-threaded architecture at the moment. But I think that's kind of good because it reduces the memory footprint and the complexity. And it's probably a good fit for a lot of really simple devices that this is targeted at. They've also done a lot of work on security. Okay, in two parts to security. They've got this idea of sandboxes, okay, within Mbed OS. So I can actually run my application out of a kind of firewalled area of memory. And so what they do is they use the MPU that's present in our 5179 Cortex-M3, and they configure it so that the application can't talk to other areas of memory, can't access other areas of memory, and it can't access a lot of the other peripherals. So basically, I'm running this secure sandbox. So I can't access cryptographic keys or algorithms from my application. Okay? In addition to that, what we can do, we can layer on more technology using our secure element, and we can put that outside our 5179 chip, and we can use that for secure key storage. Because one of the big things that everybody forgets is once I've got a device in my network at home, and I've screwed my light bulb in, okay, that's great, but same when my light bulb fails, and I go and discard it. Okay? I've just thrown away the key to my network. That light bulb contains the key to my Zigbee network, my Thread network, if it's a Wi-Fi light bulb to my Wi-Fi network. Okay, so a sophisticated attacker could then take that light bulb, reverse engineer it, get the key out, and perform some sort of attack on my home automation network. Okay? But if you use NXP secure element technology in conjunction with wireless communications, okay, we can securely store that key. And this is technology that we use in the banking industry. So this is present in chip and PIN cards, present in e-government passports, et cetera. So we've got a long history. Just kind of a little bit of an aside, but something that's overlooked, I think. So another piece of software that Mbed offer is a TLS solution. Okay, so this is, everybody probably knows, transport layer security, very similar to SSL. Okay, and they've offered this inside their Mbed client. Okay, so again, no need to go out and go to a third-party supplier of an SSL library or try and find an open source version. You've got TLS built in, so you can know that you've got secure communication from your client or your gateway up to the cloud. A lot of value add in this, because this is difficult stuff to get right. Finally, on the software side, they offer a lot of tools. Okay, so Yacht is a kind of, I always think of it as a configuration management tool. But basically, I can send my software up into the cloud, and then I can pull down all the different modules to go with it. Okay, so it's like a sophisticated cloud version of Make. And then they've got some debugging tools as well, Green Tea. And of course, you can still program online. Okay, so the original model with mBed was you program online, you compile in the cloud kind of idea. You can still do that, but also you can download and you can work locally. Okay, so that's one of the changes. We're going to move on to Thread now. So I did an interview with the media today, and it was about Thread. And the guy said to me, what happened to Thread? He goes, a year ago, 18 months ago, it was everywhere, and it's kind of gone quiet. Well, everybody's been working on it, right, in the background. And this is really, mBed, I think, is going to help launch it, okay? Having a Thread stack inside mBed. So what is it? Okay, so for the people that don't know, it's a wireless mesh networking stack designed to work on IEEE 802.15.4 radios, operating the 2.4 gig band, and it's IPv6 based. And in fact, every layer in the stack, and we'll go on to see this, is based on some sort of RFC. Okay, so it's all kind of IETF compliant, uses technologies like UDP, right? RIP for routing. So all the technologies that have been well proven out on the major internet are being brought into the Internet of Things via Thread. It's been targeted initially at the smart home. Okay, so this was a very, very clear intention, I think, of the Thread group. Whilst this could be used for commercial and building automation, industrial applications, all sorts of things, it's been targeted quite clearly by them at the home. And what they've done is, because they know that means there's not going to be installers putting these products in. So it's going to be consumers putting these products in. So they've focused on trying to make this very easy to install, very secure, but not at the price of making it more complicated to install, which is quite a feat. And I think they've done a fairly good job. Okay, so the Thread specification is managed by the Thread group, okay, which is, there's about 5 founding members, and those are the guys that define the specification. It's currently not public. The spec is not public at the moment. It's only available to members, and it's going through an iteration at the moment. So they put it out for comment to members 1.0. Members all came back with a couple of comments, so they're upgrading it. What's going to happen is going to be very similar to Zigbee or Wi-Fi or things like that, and they're going to have UL running the certification program. So you're going to build your Thread device, hopefully using NXP's platform and mBed OS, and then before you put it on the market, before you can put a Thread logo on it, you take it through certification. And they just check that you're compliant with the spec. Now, if you're getting a stack from a certified vendor, then the chances are you will be. But you still need to go through UL. They're going to test it. Then you can put the Thread logo on it. Important point is that it's royalty-free. Okay, so you have to join the Thread group to use this technology, and that gives you access to their IP. But then there's no royalty to pay per device shipped or anything like that. Just the same with Zigbee. Okay, so some more details about Thread. So 4 types of devices in a Thread network. Most mesh networking or wireless networking technologies define different types of devices, and Thread's no different. So there's a border router. This is the device that really bridges between the wireless mesh network and the LAN, okay, via either Ethernet, Wi-Fi, cellular communications, whatever it is. There's routers in the network, okay, so these are permanently powered devices that route messages for other devices in the network. So what that basically means is you can extend the range. Okay, so if I have a number of Thread-enabled routers in my home, they can all relay messages. So my one device doesn't have to be in direct communication of the border router if it wants to get onto the internet, because it can hop messages, or messages can be hopped via intermediate devices. Okay, so very similar to Zigbee. There's another class of device, and we'll talk about why they put this in there in a minute, called a router-eligible end device. A little bit of a mouthful. This is a device that can have router functionality if certain conditions are met, and we'll come on to what those are. And then, of course, very importantly, they still support what they call sleepy end devices, which are battery-powered devices. Because in all these wireless mesh networks, you're still going to have edge devices. Okay, you're going to still have devices that don't have a permanent power supply. So Thread supports those as well. Let's talk about each of those devices that we listed in a little bit more detail, try to give us a little bit of a flavor of what Thread really is. So as I said, border router, it's really like a PHY translator in a way. So it translates 15.4 on the one side to something like 802.11, Ethernet, something like that. Okay? The really important point about Thread, I think, because I always look at things and I compare against Zigbee, Thread, you can have multiple border routers in a network. So there's no single point of failure. Whereas in a Zigbee network, you tend to have one coordinator that's kind of similar to a border router, but you can only have one. And it does become a single point of failure under certain circumstances. So Thread's really good, no single point of failure when it comes to border routers. There's two types, and this comes from the spec. They see two types of kind of physical implementations of the border router. The more sophisticated version is something like maybe your Comcast box, okay? So you've got several Ethernet ports on it, an Ethernet switch at the back. You've got a Wi-Fi interface, and then, of course, you've got your cable modem interface out to the internet. And along there, you've also got a Thread interface. So you can see here, already see that we said that Thread is IPv6 based, and you can already see it's just treated as another IP interface by the application processor. And you can also have the more simple kind of version where they call it a connected appliance, but this is more of a simple bridge. If you've already got a router or something in your home that has internet access, you're probably going to build something more like this. So the Wi-Fi connects to your existing IP infrastructure, and Thread then connects to all your wireless mesh network. Some important points here we got to talk about when we talk about Thread. So we mentioned routers. I think anybody that's familiar with Zigbee is going to probably hone in on this number right here. Okay, so the maximum number of routers in the Thread network is 32. Okay, so that sounds pretty limiting at the first pass of it, right? What does that really mean? Well, it doesn't mean the maximum size of your network can be 32 devices. Actually, the kind of theoretical limit is probably is 511 devices in a Thread network, okay? Because not all of them will be routers at one time. So this is where Thread gets interesting. So we said routers. They're not designed to sleep. They route messages for other devices. And they also provide joining service, so anybody wanting to come into the network has to join via a router. But what happens with routers in a Thread network is they'll look around and they'll see how much traffic is around them, how many other routers are present in the network. And if they see above a certain threshold of routers, and there's an average signal strength above a certain threshold, they will demote themselves to what we call router-eligible end devices. Okay, so they'll downgrade themselves, saying, I'm not going to route traffic for anybody else anymore. Okay, so on the face of it, you think, why would they do that? It sounds like useless functionality. It actually makes the network far more scalable. Because in the background, routers are always transmitting messages. Even if they're not sending data from their application, even if they're not forwarding messages for anybody else in the network, they're always generating traffic because they have to maintain links between each other. They have to constantly understand the signal strength is changing. So the more active routers you have in the network, the more congestion there is. So Thread came up with this idea of routers being able to sense the network's getting congested and demote themselves to be reads or router-eligible end devices. And you can work in reverse as well. So a router-eligible end device can promote itself. Okay, so once it sees, oh, actually the number of neighbors has gone down and topology's changed for some reason, okay, it can then promote itself back up. And the nice thing about all of this is this happens autonomously. You don't know, as an application running on a Thread device, you don't know this is happening. This is all done in the layers below you. Okay, so the idea is it makes the network more scalable. So we talked about sleepy end devices briefly. These are battery powered. And the important thing about battery powered devices is they're not always awake, okay? They sleep most of the time. So what that means is you can't send data directly to them. So just the same as in a Zigbee network, they have to have a parent. That parent's responsibility is to buffer any messages. So if I want to send a message to that speaker and that speaker's battery powered, I have to send it to the speaker's parent. That speaker's parent buffers it and waits. What the end device has to do is wake up periodically and say, hey, parent, have you got any messages for me? So very similar to Zigbee. One of the key differences is I only have to wake up a maximum every 90 seconds. Okay, so I can reduce the power consumption on these end devices. Of course, they can still wake up asynchronously. If a button's pressed on them and they need to transmit a message, etc., they will still wake up and respond and transmit immediately and go back to sleep. What it does mean is that the parent of that device has to have capacity, which probably means memory, to be able to buffer at least one 128-byte message for every end device child that it supports. Otherwise, it's not going to be able to receive messages. Okay, so here's the thread protocol stack itself. What we've got the standard 7-layer model in here for reference, and this is a typical TCP/IP stack. And what we can see is it's very similar because it's an IP stack, right? That's the message, I think, really here with this slide. Although the data link and the physical layers are 15.4, over here they could be 802.11, they can be Ethernet, they can be anything. But as we start moving up the stack, we start seeing familiar names. So IPv6, UDP as the transport layer, and we'll talk a little bit about the specifics of these for thread. DTLS, okay, so that's a specific implementation of TLS, but for runs over UDP, okay? And then the really interesting conversation starts when we talk about thread at the application layer. Because what Thread have done is they've defined what they call an ingredient technology. So Thread isn't a full stack. Okay, so Zigbee has defined a full stack, right down from the data link or the physical layer to the application layer. They've defined every single layer, right from how the bits are transmitted on the air to what those bits mean to your application. Okay, Thread haven't really done that. They've said, okay, I'll go all the way up to the secure socket layer, as it were, and then it's other people's responsibility to define what happens above that. So there's a number of options when it gets up to there, and you've probably heard of all-join, okay, a Qualcomm protocol for use on IP networks. So that's one option to run on top of Thread. CoAP, Constrained Application Protocol, is another option, and that is actually inherently part of the Thread stack because it's used by part of the mesh layer, but it can also be used by the application layer. And there's, of course, an initiative by Zigbee, the Zigbee Alliance, to say, hey, we'll take they've already spent a lot of time and money defining devices, turning them into objects with parameters, with attributes, with commands. And they call that the ZCL, the Zigbee Cluster Library. So they're saying, hey, we can take all that knowledge that we've got about the type of things that you find in the home, and we can create an application layer that can run over IP, so Zigbee IP. So you could see a Thread device on the market that uses the Thread stack, but at the application layer, all the device parameters are represented as Zigbee in a Zigbee language. Okay, so that's kind of interesting in how this thing could kind of stack up and mix out in the end. So we're now going to talk a little bit quickly about joining the network, because this is where Thread differs from a lot of other technologies, I think. And they've really spent some time trying to make it straightforward but secure to get new devices onto the network. So as you said, this is targeted at smart home. Okay, so it's going to be a consumer that's buying a Thread-enabled switch or a Thread-enabled sensor, getting it home and wanting to add it to their network. That's got to be done really easily, but really securely, with devices that don't have sophisticated user interfaces. So what they've come up with is this scheme, and the key part of this scheme, really, I think, is this out-of-band mechanism. Okay, so we'll explain a little bit about what that means. So when I first want to add a new device to my network, first thing I have to do is use a commissioner device. Well, that's just a fancy word for the device that runs my control application. So usually a tablet, a smartphone, maybe a PC. So the first thing that device has to do has to go to the Thread border router and say, hey, I'm going to add a new device to this network. So in order to get that authorization, I have to put in a password. So this is a bit like joining a Wi-Fi network. If I want to get my phone onto a Wi-Fi network, I have to punch in the passcode, my Wi-Fi network, before it joins. So that's the first step. So the user would type in their password for their Thread network. Now that might already mean, you may only do that once, right? That might be embedded in the application, and thereafter, that's seamless and transparent. The next thing that has to be done is the commissioner, okay, has to somehow get the device that's being joined the master key that the Thread network uses. Okay, so the way we do this is every Thread device that's ever produced is going to have a commissioning key. And that commissioning key is going to be embedded in the device itself. But very importantly, it's going to have to be displayed somewhere on the packaging of that device. Because what happens is, as a user, I then take my device. So I've logged in, I've put my password in, I've told the border router I'm going to join a new device. I then take my new device, and I look at the password on the new device, and I type that in to the commissioner. Okay? So I type that into the commissioner, and I'm not done yet, because what they do then is, so they then both have the same piece of secret information. They then use that to exchange, to cryptographically and securely exchange the master key in the network. Okay, so it's a two-step process. Log into the border router, say I'm going to add a device, then take the commissioning key from the device, okay, and enter it into the commissioner. Now, so we talked about, oh yeah, I'm going to look at the packaging, okay, and I'm going to see the password, I'm going to type that password in. That's the out-of-band mechanism, right? So that's being done out of band. That's not being done over the air or over the thread network. Okay, that's why we call it out of band. Now, you don't have to type that in. That could be represented as a QR code, okay? Or, and this is what some of the things we're implementing, that could be NFC. Okay, so I could have NFC end tag integrated in my device here. I've probably got NFC in my phone. If not, I could put it into my border router. So then all I need to do is take my light bulb and tap it onto either the phone or the border router. So again, I've just shared that commissioning key out of band, but instead of forcing the user to type something in, I've done it using NFC, so just tap to join. Okay, so we're going to finish up with just a slide showing you our demo. Okay, showing you how all this pulls together. We're showing off the JN5179, as we remember is our wireless microcontroller, so our ARM Cortex-M3 wireless microcontroller containing IEEE radio. It's running mBed-OS. It's also running the thread stack. Okay? It's then communicating via the thread network, so wirelessly, with border router, the gateway. So in there, we have another JN5179, again running thread, again running mBed-OS. So those two devices communicate together, okay? Then we have an application processor running in there, running mbed client, okay? So this is the device that then goes out and communicates, actually, and I've got it running on my PC, communicates with the mbed device server. And this is the thing we said it was the cloud platform, but it's going to be running locally. And then finally, as a user, we've got an app that uses the web API exposed by the device server to allow us to browse and look at parameters changing down here. So what we've got on the booth is 51.7x based thread networking, okay, but using mBed-OS to do all parts of the software connectivity, okay? So we're showing how easy it is, okay? So the full solution to make it really straightforward to wirelessly connect your devices via the thread network up to the cloud. Here we have our latest version of wireless microcontroller, the JN5179 ARM Cortex-M3 based microcontroller that contains an IEEE compliant 15.4 radio running the thread networking stack. This also supports the mBed-OS. So what we're showing here in its entirety is the whole mbed IoT device platform. The idea behind this device platform is to give the user all the software they require to connect the device, something like a light bulb, a light switch, a sensor, etc., all the way up to the cloud, and in turn onto a control device such as a smartphone running an appropriate app. So how do we do that? As I said, we have the 5179 running mBed-OS. That's communicating using the thread protocol over the IEEE 15.4 radio at 2.4 gigahertz. Message gets sent to our IoT gateway. So this, in thread land, is the border router. This is the device that bridges between the thread network and the LAN or WAN network. In this case, it's providing Ethernet connectivity to the mbed device server that's running on my PC. Normally, that mbed device server would be running in the cloud, but we can instantiate it and make it run anywhere, so we have it running locally here. Final piece of the puzzle is we have a web interface. In this case, we have a browser, browsing web pages served by the device server. And as we can see, our device, our board here, is represented as a node on the network. So that device has announced itself. That information has been sent to mbed's device server, and we're now viewing that information via the cloud. So I'm going to click on the icon that's relevant to this device here, and I can immediately see the state of the buttons and the state of the LEDs. In addition, I can look at further information about the device, and I can read things like the model number and the part number. So what we're demonstrating is wireless connectivity using NXP's JN5179 wireless microcontroller, using the thread stack and mBed-OS to provide end-to-end IoT connectivity.